Hello, welcome. I'm Hans Bohm. I'm a software engineer in the Android Runtime Group, and I'm here to talk to you about how to manage native C++ memory in Android. Generally, most Android applications are written in Java today, maybe Kotlin in the future, but there are sometimes reasons to also write pieces of the application in C or C++ code. It may be the case that you can implement some algorithm more efficiently in a language like C++, or you may have a native library that already exists that you want to reuse, or the like. Here we're really talking about multi-language applications that combines, say, Java and C++. It turns out that even if you're in the business of writing 100% Java apps, as you may be, some of what I'm going to talk about may still be an issue in certain isolated cases. For example, if you look at the Android platform implementation, the big integer implementation that you're using, if you're using big integer at all, is actually implemented in terms of native code underneath. And that may, in other cases, that sort of thing may actually show through. So that was one of the reasons I got involved in this. I actually spent some time working on the Android Calculator app, which happens to be a major client of big integer. Here we're going to use a running example of a hypothetical C++ package that we want to access from Java language code that manipulates polynomials over GF2. Does anybody know what that means? Good, you're not supposed to, it doesn't matter. As far as we're concerned, these are basically bit vectors with an odd notion of multiplication, but I don't even care about that. I'm not going to show you the C++ code, actually. In this particular example is good because it turns out that in spite of the fact that it seems esoteric, modern hardware often has hardware support for this, so you can actually build a blazingly fast, really low-level implementation. So what we want to do is we have this library, and we want to call that library from Java code. So what this looks like roughly is the following. Is the code that you see up here. So the important part here is we have a Java class which logically owns a C++ object that actually contains the guts of the implementation, that actually implements the real functionality, which I'm not going to show you. What the Java object holds is a Java long, which is really a C++ pointer in disguise. There's then what it's going to do is, for example, when you want to multiply two of these, this is eventually going to call this native multiply function. It's going to pass it two Java longs. This is going to go into some JNI code, which will cast those Java longs to C++ pointers and manipulate the C++ objects. And in this particular case, return another Java long, which is really a C++ pointer. So the Java level multiplication routine is really one that just gives me back a new binary poly object containing this Java long, which really points to C++ code, which I obtained the underlying C++ pointer by calling this native multiply routine. So here's a pictorial representation of what this looks like. I have the Java object at the top of the slide, which is the only thing that my client actually sees. So I want the client to be able to treat this Java object as though it were implemented completely in Java and ignore the fact that there's C++ code underneath. The dashed line here is the Java long, which is really a C++ pointer, which sort of points to the C++ object representation, though Java doesn't know that. And inside the C++ object representation, there may be additional pointers that point to additional C++ data structures. So what's the problem with doing this? The problem comes into play when we try to think about how memory gets managed and how objects get deallocated. On the Java language side, we have a garbage collector that cleans up after us, and we generally don't have to worry about this too much. When things are no longer referenced, they go away. When they become unreachable, they go away. On the C++ side, we have a manual memory management discipline usually. which means we explicitly need to call some delete function, some deleter, in order to deallocate the memory when it's no longer reachable. So how do we actually do that? We have to arrange for somebody to call the delete function on the C++ object. So here's the traditional way to do this, and the point of this talk is largely to talk you out of doing it this way. The traditional way of doing this, which has the attraction, admittedly, that it's relatively simple to write the code compared to what I'm going to show you, is that in addition to things like the native multiply method, I'll have a native delete method to which I also pass a Java long, and then the native delete method will again convert that to the C++ pointer and invoke delete on it, or invoke the appropriate deleter on it. I will call that native delete from a Java finalizer. The finalizer is invoked more or less when the object becomes unreachable. So that then goes ahead and invokes native delete and deallocates the C++ object as well. I'll show you some reasons why this is problematic here. So I'll go through a long list of finalizer problems. Finalizers have a deserved reputation for being hazardous, and I'll only confirm that here. But I'll actually emphasize some relatively lesser known problems, which in my opinion are actually the most serious ones to try to come to grips with. And then I'll show you how to work around those. So the first problem is that if two objects become unreachable, the finalizers actually run in arbitrary order. That includes the case in which two objects that point to each other become unreachable at the same time. They can be finalized in the wrong order, meaning that the second one to be finalized actually tries to access an object that's already been finalized. I'll go into some more details there. So as a result of that, what can happen is that you can then get dangling pointers and see deallocated C++ objects. The thing to keep in mind here is that a result of dangling pointers in this environment is that you very often end up corrupting the C++ heap, but worse than that, the Java language runtime actually relies on that C++ heap as well. So when this happens, often what you end up with is also a corrupted Java runtime. And you may end up seeing caches that actually look like Java garbage collector caches or the like. So here's to illustrate how this can go wrong. Here's a sample client application that actually uses the binary poly class that we just talked about. And this in combination with the previous class will definitely break, so definitely do not do this. So what this is doing in its finalized method, it's just doing something innocuous on my binary poly, which is this field that happens to hold a pointer to the binary poly. Now the problem here is that it's entirely possible that the my binary poly object actually gets finalized first. So what you're accessing here is an my binary poly, which actually has already been finalized. So by the time you access it, the pointer, the C++ object underlying it will have been deallocated, and the native pointer that you're using actually points to nowhere. So that's a bad thing. There's a second problem with finalizers, which is actually turns out to be more complicated to work around. It's less important on Android, but is generally important when writing Java language code. So by Java language rules, and this is not currently true on Android, not currently believed to be true on Android, object X's finalizer may actually be invoked while one of X's methods is still running. So while I'm still running a method on that object may end up getting finalized. This can result in the same sort of phenomenon. I get native heap corruption and as a result, possibly Java runtime corruption. Let me explain why that happens. So here's sort of, again, an excerpt from the binary poly class. I used multiply before, I'll use it again here. So I have this native multiply method that gets called by multiply. If you look at what this actually gets compiled to, and this isn't real, this is sort of pseudocode, the pseudocode it gets compiled to looks something like this. So what happens when I want to multiply two values, I first end up retrieving the native handles from both of them. In this case, from this, and I may put this in here explicitly to make that clear. So I retrieve mnative handle from this, and I retrieve mnative handle from other. Then I might allocate the new binary poly object, and then I will go ahead and call the native method. So the problem with this is if we look at the uses of the actual Java objects, the last use of this and other actually happened before I allocate the new binary poly. At that point, from that point on, this method doesn't use either this or other anymore. And it may so happen that this is in fact the last call on those. So this is in fact the point at which those become garbage, and the garbage collector notices that they're no longer reachable. So what can happen at that point if the ABIs are designed to allow this, and if all the stars line up just right, it can in fact happen that the garbage collector at that point decides that these are no longer, that this and other are no longer needed, and arrange for the finalizers on both of those to get invoked, roughly where the new binary poly occurs. What then happens is that when we call native multiply, we don't need the objects anymore, but we still need the native handles. But now the native handles have been deallocated. So in fact, I'm accessing objects that are no longer around. This is allowed by the Java language specification, and is something that, that has been seen on rare occasion in the wild, but it doesn't happen very often. There are more problems with finalizers. You can see a lot of them by looking at Joshua Bloch's Effective Java book, which actually has a section entitled, I believe, Avoid Finalizers. One thing to indicate the problems is that it's actually, the plan is, I believe, to deprecate finalize in JDK 9. Another issue which I'll look at occasionally here a little bit is that for this to work correctly, if you run an application that allocates lots of native memory and relatively little Java memory, it may actually not be the case that the garbage collector runs promptly enough to actually invoke finalizers or the other mechanism I'll suggest in a minute here. So you actually may have to invoke these system.gc and system.run finalization occasionally, which is tricky to do because if you do it too much, it will greatly slow down your application. And many people have fallen into that trap. There's a more subtle issue that sometimes finalizers actually extend the lifetime of the Java object for another garbage collection cycle, which means for generational garbage collector, they may actually cause it to survive into the old generation, and the lifetime may be greatly extended as a result of just having a finalizer. And there are other issues, which I won't go into here. So how do you really delete C++ object? I should point out the usual advice here, which I'll skim over briefly, is to use explicit close and try with resources. So Java has a syntactic facility which allows essentially C++ style destruction. When you leave a scope, you can arrange to explicitly call the close function, and that works when it's applicable. So there are cases like file-like objects, system allocated objects, and so on, where that's generally the right approach. And that's the main recommendation. But on the other hand, there are many cases in my experience where that doesn't work. And in general, people already use this in those cases where it's applicable. So for example, if I mentioned the Java lang big integer example in the platform, you really don't want to have to call big integer.close every time one of those goes out of scope. That would be completely untenable. And there are many more examples like that in the Android platform. I should warn you that for the solutions I'm talking about here, a lot of this is actually not fully settled, and the community as a whole, this is sort of beyond Android as well, is still trying to figure out what the right way to do this is. These are mostly sort of general Java language issues that are actually not specific to Android. but there seems to be agreement that you shouldn't use object.finalize, as evidenced by the fact that it's going to be deprecated sometime in the future. So the advice here, and I'll go into how to do this, is we use something called Java-lang phantom reference instead. Many of you may have encountered that. As far as I can tell, most people look at it and ignore it because it's somewhat complicated and probably appears even more complicated than it actually is. It's not very commonly used, but it actually is a better replacement for finalizers. It avoids the problem that the finalizer can see finalized objects because of the ordering issues. Phantom references ensure that you run the cleanup code only when the object really is about to go away and nobody can use it and nobody can see it anymore. It certainly deals with the finalized deprecation issues. It's not going away. It also ends up dealing with some of the more subtle issues there, though not all of them. It does not deal with the premature cleanup issue that I mentioned earlier, that an object can be finalized while one of its methods is still running, for example. The major difficulty with using it, and I'll go through an example here, is that it's relatively complicated to use at the moment. And we're in the process of making that better. I think various groups are in the process of making that better. So Java 9 actually has this notion of a cleaner, which makes this a little bit simpler. Inside the platform, we actually have something called native allocation registry that deals with some of this. This is at the moment not a public API, but if you're interested in this, we're trying to assess whether it would be good to make that a public API, or whether this is the right API to do that with. So what should you use instead? Well, I mentioned these phantom references. So what are they? A phantom reference is shown here with the ghost next to it. It's an object that's associated with the object whose lifetime you want to monitor. So it doesn't actually point to or refer to the binary poly object that we want monitored and then we want to be cleaned up after. So you can sort of think of the phantom reference as the last will and testament of the Java object. It tells you what to do, how to clean up the object once the Java object dies. So both the way this works normally, in order to actually use a phantom reference, you'll usually inherit from it, and the inherited derived class, the class derived from phantom reference, will have a pointer to the C++ object along with the Java binary poly object. There's also a reference queue off to the side here, which I'll show you what role that plays in a second here. Notice that I've put those ground symbols in here in a few places to indicate that those are objects that we need to make sure don't get garbage collected. So we need to have some mechanism for keeping those around. That applies to both the phantom reference and the reference queue. So what happens after binary poly becomes unreachable? The phantom reference itself gets added to the associated reference queue. And that's basically all that happens. The Java object gets immediately collected. There's no longer any need for it because the phantom reference itself knows how to clean up. So I'll show you a sort of quick implementation of this here in this case. This part actually is fairly easy. So we've modified binary poly to deal with this sort of reference cleanup. And what I've done is on the next slide, I'll show you a BP phantom reference implementation that inherits from phantom reference. It's a kind of phantom reference that's specialized with some additional functionality here. And what this does here is we still have the native delete method that actually deallocates the C++ object. Whenever I allocate a binary object, I now do it through this factory method, which constructs and allocates the object, but then immediately goes and registers it through a static method in BP phantom reference, the way I've implemented it here. Now, what's BP phantom reference? So that fits on a slide in the same way that, in the sense of the old Midas commercial, if you remember that. So, I've stretched it to fit it on a slide here. So what that does is it introduces a couple of static data structures. One of them is the actual reference queue, which will be used to enqueue these BP phantom references once the corresponding Java object is no longer needed. And I also need to have a concurrently accessible set here, some way to just keep the BP phantom references around so they don't get garbage collected themselves. So I just keep those around as long as, basically until they're explicitly removed. So what I do then is whenever I construct one of these BP phantom references, I first of all construct the phantom reference, giving it the Java object and the reference queue. So that this tells the underlying phantom reference implementation to watch that Java object and put it onto the queue that I gave it when the Java object goes away. And then I also remember the native handle so I can actually invoke the deallocation function when it's time. So what happens when I register one of these things? So I register a Java object and the corresponding native handle. I create a new BP phantom reference, and I add it to my set here just to make sure that it doesn't go away. And this is sort of part of the ugliness of the scheme, unfortunately, that we're trying to address. At some point, every once in a while, I actually need to arrange that everything that's on the reference queue gets deleted. And I've done that here by providing a method, doDeletes, which just checks whether there's anything available for deletion, and if so, it goes ahead and deletes that. In other contexts, you may want to do this differently. Rather than just polling whether something is available, you may actually want a separate thread for this and block. It sort of depends on the context. It's a little bit tricky here to do this well in a large system because the easy way to do this is to create a new thread for every class that does this, which may or may not be acceptable depending on how many of these you have. So then, in order to actually make this work, my application needs to do the following things periodically. In simple cases, you can skip the system.gc and system.run finalization. If you notice that the garbage collector isn't running enough because you're not allocating enough Java objects in order to actually trigger it, you may have to explicitly do that, but usually that's not an issue. But you do have to regularly call BP phantom reference.doDeletes to actually do the cleanup the way I've done things here. So the next problem here that I mentioned is the premature enqueuing while a method is still running. As I said, this is not actually an issue for Android, but it is an issue for portable code. So there's a partial solution to this in Java 9, which is this thing called a reachability fence, which you can explicitly invoke to tell the implementation, don't let the argument go away yet. It's still live it should still be live to the garbage collector, even though it might not look like it. That's not really available basically in any implementation that you can use at the moment. So the best solution that my colleagues and I could come up with at the moment is the following, which is relatively simple but not exactly performance neutral, is that instead of having simple methods like multiply that just invoke the native method with the native handles, what we do instead is we invoke the native method with both the native handles and the Java objects. So what I do instead is I have a native multiply that takes the two J objects as well, and current implementations, though the spec doesn't 100% guarantee that, current implementations are essentially guarantee that this and other turns into a local ref, which tells the garbage collector to keep these around as long as the native method is running, so things will actually work out correctly at the expense of passing additional parameters through JNI. Again, this is recommended if you have to write portable code. For Android, I currently wouldn't recommend doing that. Eventually, sometime in the future, I think we will probably have a better solution to this. So one more hazard that I want to go over quickly, in part because this actually, this is near and dear to my heart because it took several months of several people's time to debug platform code that had this issue. If you're using C++ code in this way, you need to be really careful that you're actually calling it correctly and not violating the C++ rules underneath. And that can be quite tricky to do correctly. So in particular, if you're calling C++ code from Java threads, it still has to be thread safe as though you were calling it from multiple C++ threads. And you have to make sure to follow those rules. This is a bit aggravated by the fact that some Android framework classes actually use C++ code internally. So this gets back to the point I was making at the beginning, that you have to make sure to use those frameworks classes correctly, because otherwise you can run into this problem even without actually writing native code. One issue that's particularly subtle on the C++ side that actually contributed to this problem that we spent lots of time on is that often on the C++ side, when you call delete, you actually end up invoking some reference counting mechanism that then takes care of the underlying C++ objects that I indirectly referenced. You have to be really careful in doing that correctly. I highly recommend using an expert-developed implementation of reference counting, not to roll your own. I spent a lot of time recently fixing bugs in Android platform reference counting implementations. So it's not too likely, I think, that most people will get this right, implementing it themselves. There are a whole bunch of different issues here having to do with memory ordering bugs and self-assignments and so on. It only is a tiny amount of code, but it's a really tricky piece of code. But assuming you have a correct reference counting implementation, it's still hard to use it correctly. So one thing you have to remember, for something like, the rules vary a little bit depending on the implementation, but for something like std shared putter, when you create a shared putter to something, the object will be deallocated when the reference count associated with copies of that shared putter goes to 0. So creating multiple shared putters to the same underlying, corresponding to the same underlying bare pointer is not likely to work well. It's also not likely to work well to generate a reference counter pointed to this in the constructor for a similar sort of reason, because probably by the time you leave the constructor, that reference count will have gone to 0, and you will deallocate the object before you ever leave the constructor, which is not good. So you have to be careful with that sort of thing. The thread safety rules are in some ways even more subtle and also something that you really want to watch out for. So assuming here I have a bunch of shared putters, it's actually okay according to the normal C++ thread safety rules if I take X, the shared putter X, and copy it simultaneously in 2 different threads to 2 different other pointers. This will try to simultaneously update the reference count associated with X, but that's okay. It's the implementation's job to make sure that that works correctly. So that's fine. What's not fine, and what in fact caused the sort of long-standing bug that we had to deal with here, is the last thing on the slide here, simultaneous assignments to the same reference counted pointers. If I simultaneously assign even null to the same reference counted pointer, that looks pretty benign. I'm assigning the same thing concurrently to 2 different threads. What could go wrong? The problem is it's disallowed by C++ rules for good reason, because what happens here is both threads will try to simultaneously deallocate decrement the reference count associated with the original value of p. If they race each other just right, so they both do this before either one actually assigns null to the pointer, they will end up both decrementing the reference count, which originally had a value of 1 because it was referenced by p. That doesn't go well. An extra reference count decrement is always death. So summarizing here, important point is avoid finalization. Use Java-Lang phantom reference instead. Currently, that's a little bit clumsy, but it avoids you all sorts of potential headaches. if you want to read up on this more, I suggest you actually look up the Java 9 reachability fence construct and discussion. That'll give you a little more insight as to why why some of these things are a problem, in particular why you have to worry about premature cleanup with the Java semantics. Again, not so much on Android. And stay tuned for future improvements in this area here. If you allocate a lot of C++ objects, if that's where most of your heap space ends up getting spent, then you should think about explicit GC triggering. But doing it very carefully. Make sure you keep track of how much C++ memory you've allocated, and when you've allocated a lot so you think it might be useful, then you can invoke the garbage collector, so phantom references for dead objects get enqueued at that point, so you can actually do the C++ cleanup at that point. Otherwise, if you're not allocating any Java memory, usually the Java garbage collector will not otherwise get triggered. Be careful with C++ memory management and understand the rules. So we actually have a little bit of time for questions here, if there are any. That's the end of it. Thank you very much for attending.